Welcome to this explainer. Today, we are unpacking the monumental mechanics and absolute engineering marvels behind offshore energy gathering systems. If you've ever found yourself wondering how all that colossal infrastructure out in the deep ocean actually functions without tearing itself to pieces, well, you are in exactly the right place. Think about this for a second. What is the ultimate macro problem here? How do you hold a floating skyscraper, an FPSO vessel, perfectly in place without snapping its vital connections, especially when it's being hammered by the sheer, unbridled fury of a 100-year storm? It's an incredibly complex balancing act of enormous weights, extreme tension, and precise fluid dynamics. To answer that, we're going on a bit of a deep dive. First, we'll look at mastering the mooring problem, then the specific components of deepwater mooring, and how turrets and swivels enable a neat trick called weather vaning. After that, we'll cover safe offloading with cowl buoys and wrap up with risers and flow assurance. Let's get right into it.
Section 1. Mastering the mooring problem. Let's start right at the foundation of the whole operation, the physical tethers keeping the ship from floating away.
Look at the setups we typically use to tie these ships down. You've got static spread moorings, where lines essentially anchor out in all directions to lock the ship in a fixed position. But contrast that with the dynamic genius of single-point moorings, or SPM, where all the anchoring lines converge at a single point, like the bow or an internal turret.
This brings us to a really crucial concept called weather vaning. By tethering the vessel at just one single point, it is totally free to rotate, exactly like a wind vane on a roof. The ship naturally swings its bow to point directly into the oncoming wind and waves. This is a massive deal because it dramatically reduces the environmental forces battering the hull and takes a huge amount of stress off the fragile risers coming up from the seabed.
So, why choose one system over the other? It literally comes down to geography. If you're drilling in deep but mostly calm environments where the weather is omnidirectional, places like West Africa or Brazil, a spread mooring is cost-effective and does the job perfectly. But what if you're in the North Sea? Out there, violent storm directions change seasonally. A fixed ship would just get torn to shreds. For those harsh environments, a single-point mooring turret system isn't just an upgrade, it's absolutely essential.
And you know, the engineering design standards for these tethers, specifically the API recommended practice 2SK, are totally uncompromising. Engineers have to design for what's known as the intact -1 condition, meaning if the unthinkable happens and a mooring line completely snaps during a 100-year storm, the remaining intact lines must still hold that ship with a minimum safety factor of 1.67. Imagine your car's parking brake still holding your car perfectly even if half its cables were suddenly sliced in half. It is that level of over-engineering.
Moving right along to Section 2, Components of Deepwater Mooring. Let's look at the actual hardware required to pin this massive ship to the seafloor.
A deepwater line isn't just one long, heavy chain. It's a clever composite system. At the very bottom, resting on the seabed, you have a heavy 120mm studless chain. That sheer weight creates a curved, catenary shape that gives the line a spring-like restoring force. But if you use solid steel all the way up through thousands of meters of water, the sheer weight of it would literally sink the ship. So for that massive middle section in the water column, they swap to lightweight polyester or wire rope. And finally, it's pinned into the earth using giant anchors, often these massive steel cylinders called suction caissons that practically vacuum themselves into the soft, deep ocean clay.
When these giant chains finally enter the ship's turret, they are pulled incredibly tight, and I mean tight. Before the ship even gets hooked up, these lines are pre-tensioned to 80 to 100% of their maximum design storm tension. They have to eliminate all the slack because if a line was hanging loose, a sudden massive wave could create a violent dynamic snap load, breaking the chain entirely. They basically turn the whole mooring system into a tightly coiled spring.
Okay, Section 3, Turrets and Swivels. This is where the stationary ocean floor meets the spinning ship, and it is fascinating.
If you look inside an internal turret, there's a central yellow cylinder that is completely locked down to the seabed by those mooring chains we just talked about. It does not move an inch, but the purple structure around it, which is the hull of the ship itself, rotates freely around that central cylinder on these colossal heavy-duty roller bearings. Keeping the turret internal like this totally shields the crucial connections from wave impacts.
But here is the ultimate billion-dollar engineering puzzle. While the ship is constantly spinning around that fixed turret, it has to continually suck up high-pressure oil and gas. How on earth do you pass fluid from a stationary pipe into a constantly spinning pipe without just twisting it until it bursts? The answer is this absolute beast of a machine, the swivel stack.
Sitting right on top of the turret, this towering stack uses an incredibly complex series of high-pressure rotary seals to route multiple fluid streams at the same time.
Think about the intensity here. You've got production fluid rushing in at 200 bar and gas being injected at an insane 400 bar, which is like the pressure you'd feel 2.5 miles underwater. This stack has to channel all that pressure, plus water, methanol, and electrical signals, spinning 360 degrees non-stop for 20-plus years without leaking a single drop. If a swivel fails, the entire production of the ship is done.
Section 4. Safe offloading via comm buoys. Now that we have all this highly pressurized, processed oil on board, how do we safely hand it off to get it to market?
You definitely don't want a massive transport tanker bumping into your billion-dollar processing ship in rough seas. So the industry relies on a catenary anchor leg mooring, or comm buoy. It's a large steel buoy permanently anchored to the seabed a really safe distance away from the main FPSO, connected by a floating export hose.
So when a shuttle tanker rolls up to collect the oil, it doesn't even get close to the main ship. It just moors right at the comm buoy. This setup is a total game changer because it allows the shuttle tanker to safely weather vane independently from the main vessel. Because they aren't directly tethered to each other, they can safely keep offloading oil even if there are 50-mile-per-hour winds and 18-foot waves.
But storms happen, right? What if the tanker drifts too far? Inside that floating hose is a brilliant failsafe called a breakaway coupling, with the Gall-Thompson design being the industry standard. It's held together by precision-engineered titanium bolts. If the tension goes past a safe limit, those bolts snap automatically. The split second they break, internal sealing pedals slam shut on both sides of the hose. A few drops might spill, but you entirely prevent a catastrophic high-pressure oil spill. Finally, Section 5, Risers and Flow Assurance. Let's zoom all the way back down into the dark water to check out the deep-sea veins of the operation.
Before the oil even begins its journey up, engineers have to solve what's called flow assurance. Down on the seabed, the pressure is immense, and the temperatures are basically freezing. Under those extreme conditions, water and light hydrocarbons can instantly form these icy crystals called hydrates, or waxes can solidify, literally plugging a pipe solid in a matter of hours. To fight this, they constantly pump down thermal insulation and chemicals like methanol to ensure the crude keeps flowing smoothly.
And when that fluid does travel up to the wildly bouncing ship above, it can't just be through a straight, stiff pipe. That would tear apart immediately. So engineers use flexible, layered pipes arranged in deliberate slack shapes. Depending on the depth and the waves, they might use a free-hanging catenary shape, or they attach buoyancy modules to force curves like the steep S or lazy wave. These specifically designed curves act exactly like massive subsea shock absorbers.
It's really something to see. You've got this beautiful synchronization in the subsea network where these flexible risers gracefully snake their way up from the ocean floor to the turret. It's a perfect marriage of advanced polymers and metallic engineering, built specifically to roll with the ocean's unbelievable, unpredictable power while feeding the ship non-stop. Which leaves me with one really fascinating final thought. We figured out how to master the 100-year storm today using things like precisely tensioned chains, spinning swivel stacks, and breakaway valves. But as global demands push our energy production into even deeper, darker, and crazier oceans, what kind of extreme engineering are we going to have to invent next? How are we going to tether tomorrow's floating giants? It's going to be absolutely amazing to see. Thanks for hanging out with me for this explainer, and keep questioning how the incredible world around us is built.